And here's our last example of how we deal with statics problems using the concept of the Newton's laws of motion. Again, nothing is accelerating, nothing is moving, so we know that the sum of the force in the x and the y direction must add up to 0, so we can be assured that the sum of the forces in the x direction add up to 0, and the sum of the forces in the y direction add up to 0. Now, the reason I put this little example here is that it looks kind of strange, but you'll see in just a moment that it's done just like all the others. We need to find all the x and y components of all the forces. We can see that here we have a force acting downward. Let's call that T3, which is equal to mg, the weight of this object. Here we have tension 1, which is pulling to the left, and we have tension 2, which is pulling up at an angle. Notice that the angle there is 45 degrees. And then right away, we want to go ahead and take T1, not T1, but T2, and divide that into its x and y components. So notice here we have T2 in the x direction, which is equal to T2 times the cosine of theta. And here we have T2 in the y direction, which is equal to T2 times the sine of theta. So now we can go ahead and plug all our components into our equation. In the x direction, we have two components. We have T1 to the left, we have T2x to the right. So we can say that this is equal to T1 or minus T1, because that's in the left direction, negative direction, plus T2 times the cosine of theta. For the y direction, we also have two forces. We have the component of T2 and we have T3. So this is equal to T2 times the sine of theta in the positive direction minus mg in the negative direction. So now notice that in this case, it's actually a little bit easier. We can look at our second equation and notice that there's only one unknown in there. So we can use this equation to solve for T2. If we do that, we get T2 sine of theta is equal to a positive mg. When we move the minus mg over, it becomes positive mg, and then we turn the equation around. So we have T2 is equal to mg divided by the sine of theta. Let's go ahead now and plug in all the numbers that we have. We have 2 kilograms times g, which is 9.8 meters per second squared, and divide the whole thing by the sine of theta, theta being 45 degrees, so we take it as the sine of 45 degrees. So that will give us the value for T2. So we have 19.6 divided by the sine of 45 degrees, and that's 27.7 newtons. So 27.7 newtons, which is the force attributed to T2, so that's the magnitude of T2. So now to find T1, we can use the first equation. We can use this equation right here. Let's solve that equation for T1 by moving that over to the other side. So we have T1 is equal to T2 times the cosine of theta. We know that theta is 45 degrees. We found T2, so this is equal to 27.7 newtons times the cosine of 45 degrees. So times 45 times the cosine equals, and so we have T1 equal to 19.6 newtons. All right, so now we have T2, which is 27.7 newtons, and T1, which is 19.6 newtons. So notice that T1, all it does is pull the mass to the right, keeping it from hanging straight down from the point where it's attached right here. That required 19.6 newtons, but T2 is still carrying most of the weight, so we have 27.7 newtons attributed to the tension in T2. And that is how you do that problem.